Dear distinguished guests, we are about to start the opening ceremony of the 22nd International Meeting of Information Display, IMID. Please cooperate to take your seat around, and we kindly request that you turn off your cellular phones or make them in a silent mode before we begin. The opening ceremony will be start very soon. Dear guests, please cooperate to take your seat, please. Okay, now it's on time. Good afternoon, ladies and gentlemen. Thank you for your participation in IMID 2022. My name is Byung-doo Jin from Dankook University, Executive Chair of this year's IMID. It is my great pleasure and honor to welcome all of you to this conference. I would like to thank every one of our participants for coming to this opening ceremony. I would like to begin by introducing our first addresser for the welcoming speech, Professor Sang-hee Go-Park, the General Chair of IMID 2022 and the President of the KIDS. Please give her a round of big applause.
Thank you, Professor Jin. So good afternoon, ladies and gentlemen. Welcome to IMID 22. So this is Sang-hee Go-Park, the General Chair of IMID. On behalf of the IMID Organization Committee, it is my great honor to extend our warm welcome all of you. I'm so happy to see you finally at this place during long-lasting COVID era. I really appreciate for your participation, especially those who have traveled from foreign countries to endorse. I'm sorry. From the foreign country to attend this special conference, and those who have provided great endorsement for the IMID 2022. So this time, IMID is being held as an on-off hybrid format for participants who cannot attend to in person. First of all, I would like to thank all the committee members of this conference. Without their tremendous effort, this conference wouldn't be amazing like this. So as you may know, the IMID conference is getting bigger this year, especially the IMID 2022 will include prestigious keynote addresses, invited talks, regular session, tutorial, and workshop, and also the Young Leaders Conference and Women in Display session. The technical program of 16 topics were designed by the hard work of all the program committee members. So I really appreciate their dedications. In addition, many sponsors and exhibitors have supported IMID to be a successful event. So we would like to express our sincere appreciation for your participation and support. The special exhibition will be open to everyone for free. So please enjoy exhibition seminar sessions, recruiting booths, and the demo presentation booths, and also the cutting-edge display technology in the special sessions. I hope all of our participants take this opportunity to have a deep and profound discussion on every field of information display, and also make a lasting friendship and the new colleague with all of our outstanding research. So lastly, I really want to appreciate the engineers and the scholars from the abroad who made a long journey to participate in this conference despite of this hard time with COVID-19. So thank you very much. So enjoy this conference. Thank you again. Thank you.
Thank you, Professor Sang Go Bak, for giving us the kind and warm welcoming address. And for the next addresser, we had invited the current president of SID, Dr. Achin Vlomik. However, due to the COVID-19 situation, he will give a first congratulatory address as a pre-recorded video. Please give a round of applause for his addressing message.
Greetings, everyone. I am Achin Vlomik, President of the Society for Information Display. In partnership with the Korean Information Display Society and the Korea Display Industry Association, SID is proud to be a co-organizer of the International Meeting on Information Display, IMID. On behalf of SID and the organizing body, I would like to extend my warm welcome to all of you to the 22nd IMID, being held in the beautiful city of Busan, Korea, as well as in a virtual format. This is an exciting time for the imaging and display technology ecosystem. We are at the onset of an era where human interfaces to technology is increasingly becoming immersive and interactive. Centered on the theme of driving display to the future, this year's conference presents a very rich program. Keynote speakers include the top leaders and innovators from the industry and the academia. The tutorials and workshops are taught by leading experts in the field. The sessions include an impressive array of papers. I congratulate the IMID Program Committee for the excellent job in pulling together this program. I hope you enjoy the conference, have a great time in both learning and networking, and I hope to see you all in person next year.
Thank you very much. Now, please put your hands together for our long-time sponsor, great sponsor, MOC, Dr. Woo-Kyu Kim, Managing Director of MOC Korea. He comes up to deliver our second congratulatory address. Please welcome him with a big round of applause.
Greetings, everyone. Thank you very much for inviting me to this IMID 2022. I'm very honored to welcome all of you. It's a great pleasure for me to be here at BEXCO. Taking this opportunity, I would like to express my sincere gratitude to the International Information Display Society and Korea Information Display Society. It's been almost 3 years since we were together physically in full-scale conferences. 3 years, right? Time flies. I'm very happy to see that IMID is taking place once again in full-scale, face-to-face format. However, still high numbers of cases are still out there, so let's be careful during the conference, but enjoy the conference. I had a lot of section information with me, but they were already introduced nicely by previous speakers, so I will not repeat that. But these are very special sessions. Please feel free to join and enjoy and get the insights of new display technology. And also, I'm sure the exhibition will offer companies and institutions great opportunity to network together to generate business opportunities going forward. Finally, I would like to congratulate all of the award honorees with my deep appreciation for their strong contributions with their pioneering studies, results, and knowledge on the information display. This year, I'm especially happy to have Michael, my global manager, is participating as one of the keynote speakers. So he will talk about a special topic, and he will be also joining me later for the award ceremony for MOC Award honorees. I wish all of you have insight into our digital living through conference, and IMID have lots of success throughout the conference. Thank you very much.
Thank you, Dr. Kim. Thank you for your great congratulatory message. Now, as a next step, MOC Award will be presented. To deliver MOC Award, please welcome Dr. Michael Heckmeyer, Executive Vice President, Display Solutions of Electronics Business of MOC, KGA, with a nice applause. We would like to present MOC Award recipient first. The winner of the MOC Award is Professor Yong-Yong No of POSTECH. He's also program chair of IMID this year. Please give him a big round of applause. Professor Yong-Yong No, in recognition of your achievement of high-resolution patterning process, large area printing, and high-performance semiconductor ink, perovskite, and metal halide semiconductors for high-performance thin film transistors. Congratulations. Photo. Okay, we will take another photo later. Next, the winner of the MOC Young Scientist Award is Professor Seokju Kang of Seogang University. Please give him a big round of applause. Professor Seokju Kang, in recognition of your research on an image and video quality enhancement system for next-generation display, as well as high-speed deep learning-based super solution architecture design. Congratulations. Now, photo. Now we will take the photo together. Two recipients. Congratulations again, and thank you very much, Dr. Kim and Dr. Ekmeyer. And now, please welcome again the General Chair and President of KIDS, Professor Park, up to the stage again for our Achievement Award ceremony. She will give the Achievement Award of IMID 2022 to the recipient. The first Achievement Award of IMID 2022 goes to Professor Byung-ho Lee of Seoul National University. However, due to his current circumstance, Professor Jae-hyung Park of Inal University will be given the award instead of him. Please give him a great round of applause. I will read in Korean. 비학께서는 이병호 교수님, 비학께서는 디스플레이 기술 개발 및 산업 발전에 크게 기여해 주셨을 뿐 아니라 본 학회의 발전과 활성화에 헌신적인 노력을 다해 주셨기에 그간의 노고에 감사드리는 마음을 담아 이 상장과 부상을 드립니다. Congratulations. Now, photo. Congratulations, thank you. Another next achievement award goes to Dr. Julie Brown of Universal Display Corporation. Please give her a warm applause. Certificate of Special Recognition presented to Dr. Julie Brown, Universal Display Corporation, in recognition of continuous contribution and strong support to KIDS. Sang-hee-go Park, President of the Korean Information Display Society. Congratulations. Now photo with Now two recipients of the recognition award, take a photo together, please. Julie, would you like to take a photo together? Thank you. Okay, thank you so much. Thank you, President. Now, please get ready to show your best applause for our technical program chair while he come up to stage to deliver our technical program committee report. Professor No, please come up to the stage.
Okay, good afternoon. My name is Yong No, postdoc. I am a program chair of IMID 2022. So I will give a brief introduction of a technical program of IMID 2022. Okay. So this year IMID, actually we have two event, tutorial and workshop held in Tuesday. And then actually more than 300 people actually gathering together to listen tutorial and workshop, and also more than 10 actually talk given tutorial and workshop session. And the main conference from today to Friday, and we have 4 distinguished keynote address will be given soon after this and the opening ceremony. And also we have 64 sessions, including Young Leaders Conference 1, 2, and Merck Science Connect, and Women in Display. And the Young Leaders Conference will be held this Thursday and Friday, and also Merck Science Connect also will be given tomorrow actually afternoon from 4 to 5:30. And also Women in Display session will be given and this Friday in lunchtime, and also we will serve the lunch box for their networking and a connection. And also we have more than 450 poster presentation will be given every day from Wednesday to Friday. Okay. Next slide. Sorry. Okay. Then we have a very nice actually exhibition and special exhibition which also just start before, and then actually it continues going to the Friday and the main hall in the exhibition center. And we have the 18 seminar from the company in the exhibition site, also the 5 company held in the recruiting booth to recruiting young scientists and further their display company. And also 6 demo presentation will be given, and also the special exhibition more than 70 company is actually prepared. This is the list of company that make booth in the exhibition session. And also the list of company actually participating in the exhibition session. And let me talk about the paper submission number and also the statistics. And this year in this event, more than 750 abstracts actually submitted and 60 topics. And we have 3 special sessions, and then also the regular session is total and 16. And also the total number of paper is submitted is 750, then including 10 featured invited speaker and more than 110 invited speaker, and also more than 200 oral speaker and the poster speaker as well. Okay. Then also the total 730 paper will be presented from today to the Friday, and also this is number of featured speaker and the invited speaker and oral speaker and the poster speaker as well. Also there is some many award actually paper will be presented, and for example Merck Award winner also will be given the talk in Merck actually connected session, and the Kim Yong-bae Award actually winner also will be given a talk in Kim Yong-bae Award session, and Young Leaders Conference also will be given. This is actually total number of paper actually will be present in the conference this year IMID. Okay, paper was submitted more than 36 countries from all around the world, and the highest country is Korea and Japan and United States and China, and also other many actually country actually submitted the paper. But unfortunately, due to the COVID-19, as you know, then therefore, and the number of paper is from other country a little bit lower than the previous and the ordinarily condition, but we hope actually they also enjoy the conference online, offline as well. And also many actually international committee members attending to review of our paper. So more than 210 reviewers from 40 countries attended together to actually technical and program and the reviewing. So then actually number of reviewers for each session is like this. Then therefore, and the paper selection meeting and this year May, and we selected a very nice paper to given in this IMID conference. Also, we actually designated the award winner during this paper selection meeting. Okay, we have 3 special sessions, and first one session is AI and computational technology for display, and the second special session is display with a free form factor, and the third special session is a hyper-realistic display for metaverse. Also, poster session actually will be given from today to the Friday, and in the mid-time, and as you check their poster time, and poster session will be given in exhibition site. So therefore, in the center of the exhibition site, you can find the poster session. So please enjoy the poster session. Also, the Best Poster Award ceremony will be given after the poster session, so you can actually also attending the which poster get Best Poster Award. And the Young Leaders Conference will be held on Thursday and Friday. There are 2 kinds of Young Leaders session. First one is actually presented by the fresh PhD and postdoc and the professor, a junior professor, will be given their talk, and the first Young Leaders Conference. And second Young Leaders Conference presented by the distinguished student, then they will give a talk from Friday afternoon. Then also you can vote which talk is the best in the session room in the Young Leaders Conference 2. Then therefore selected paper will be given and award. And this is a final special thanks for the sponsor of our IMID. Without their help, we cannot preparing this wonderful event. Thank you for this nice response. Thank you very much for your actually attending this conference. Thank you.
Thank you, Professor No, for delivering the most informative and nice TPC report. Actually, it is a great program until the end of the conference Friday. But now, I know that everyone is looking forward to see, and this is our most interesting part of the conference, our keynote speech session. Please show us how much you get excited through your great applause. Again, to Professor Young No, session chair of our keynote sessions.
Okay, it's me again. And, I'm actually chair of keynote session. Let me introduce first our keynote speaker, Dr. J.S. Cho, Samsung Display Corporation. Please show your big round of applause for welcome him. So let me brief introduce Dr. J.S. Cho, Samsung Display Corporation, before his talk. Okay, he have received his PhD degree in electrical engineering KAIST. After then, he joined to Samsung Electronics, and year 2006, he was a VP and head of DRAM Team 3 memory business Samsung Electronics. And year 2011, he promoted to the executive vice president of head of DRAM development center and memory business Samsung Electronics. And after then, year 2017, he also promoted to the executive vice president of head of America office DRAM DS division of Samsung Electronics. From 2020 December, he became a president of CEO of Samsung Display. Today, he's going to talk about changing display industry with disruptive innovation. Please show you a big hand to welcome Dr. Cho.
Thank you, Dr. No. As I'm getting older, it's very hard to speak with the mask. Please understand. I did the PCR test this morning. It's a negative. It's a good afternoon, everybody. So I'm J.S. Choi, the president and CEO of Samsung Display. I'm very excited to be invited at the IMID 2022. And it's my great honor to open this event with my keynote speech. I hope today's event to be a meaningful venue for academia and also the industry to share collective vision of display. I spent most of my time in semiconductor, 28 years, and just joined this display. I totally forget about what I have done before. I totally focused just on display. We will survive. Is within 10 years, you will be seeing different perspective of display industry, I bet. So, can you go back? All right, let me start. Nowadays, it's not so surprising to see the world where the virtual platform is more natural than the physical world. And working at home became part of employees' life. But only a few years ago, such a world looked like awkward and distant future. For the past 3 years, as the world lived through the pandemic together, new forms of lifestyle were quickly immersed in all areas. That included work, social, entertainment, and healthcare. When the pandemic comes to an end soon, some people will return to workplace and school. But the structural transformation from the physical to the virtual world will not stop, but continue. And this is where display plays an important role as a window that connects to the physical and to the virtual world. But this is not the first time display leads changes in consumer lifestyle. Let's looking back. Display has played a dominant role in consumer lifestyle. The innovation began from large display like TV and monitor. The video content innovation in the 80s was enabled by color CRT. In the 90s, people could use a computer on the move, mainly thanks to the development of flat panel LCD for IT. In the beginning of the millennium, larger LCD opened the era of flat TV and monitor. Thereby, it reshaped living room and workplace. At the turn of 2010s, display innovation expanded to mobile display, and it provided clear image quality in a compact design. Meanwhile, so high-resolution OLED opened the era of mobile computing. It's like this. Everybody has this, right? And now, we stand at the doorstep of opening a new era for AR and VR display. That would be the ultra-small display with the hyper-realistic image quality. Shortly, display has overcome the limit of pixel from large size to small size, and also they are in the middle of evolution where display of all size become hyper-realistic. Then, which technology will shape future display? To answer this question, we have to understand what's going on in the market these days. After smartphones dominate a decade, I believe the divergence of device is taking place. Because we have to meet the segment and evolving needs of customers in the era of divergence, seamless experience matters as multiple devices are used and also being connected. Users want to experience the same image quality of the smartphone OLED on their laptop. OLED with deep black, realistic color, and clear motion will make it real. Also, the era requires various form factors to meet their own personal needs. In terms of content production, development of software and OTT are upgrading picture quality and also standard. Not long ago, we held a showcase in the US where I had a chance to invite Hollywood movie companies. At that time, I introduced our new product, QD, and listened to their opinions. They expressed great interest in the self-luminous QD display, praising it as an incredible performance. The transition to the self-luminous display is natural because it fits well with all these emerging trends. All right. Do you remember 2004? Samsung Display announced world first investment in Gen 7 LCD and also declared to break 100 million unit threshold of LCD TV by 2010. It's just in 6 years. Many had a doubt about our ambition because then LCD market was only about 15 million units. However, the market surpassed 100 million threshold in just 4 years. And it continued explosive growth to reach 20 million units in 2010. In the OLED business, Samsung Display started mass production of the Gen 5 line. At that time, we declared our ambition to replace the whole smartphone display with OLED. Nobody believed. But since then, driven by the remarkable growth of the OLED business, OLED now has taken up almost 70% of the smartphone revenue in 2021. It's amazing. Adieu, LCD. Goodbye, LCD. Welcome, OLED. Recently, Samsung Display totally exit from LCD because it's time to be smart and also proactive. We believe this is the time to move forward rather than stick to history of LCD. Meanwhile, Samsung OLED business has grown steadily since its commercialization in 2007, and now prepared for the full bloom of self-luminous display. For just past 3 years, Samsung Display has consolidated the core technology for diverse OLED applications. Built upon the success in smartphone, we are going to create another success in IT, like notebook, automotive, and also gaming. And we will identify your application area very proactively. Once again, This is the time to move forward. I hope the entire industry wisely face this turning point and regain our position. Display industry would be as much important as semiconductor. Throughout the pandemic, the self-luminous display market grew by $15 billion in just 2 years. Considering the trend of self-luminous display, it's fair to say the market has entered a new growth zone. The self-luminous display market is forecast to value about $40 to $45 billion this year. To have positive outlook, I expect the self-luminous display market reaches $100 billion before 2030. It won't be impossible if you think about examples in the past. Samsung Display is on the challenge of joining the $500 billion club. That's uncharted areas, even for an industry-leading company. But how can we bring this ambition into a reality? So we at Samsung Display have decided several key projects to reach mid to long-term target. Here in Busan, you may not know, I was born in Busan a long time ago. This is my birthplace. I'm going to announce Samsung's big plans. First, we decided to huge invest in production line for Gen 8 IT OLED. And the mass production is scheduled for 2024. Second, we plan to have a deep dive into the IT and automotive business, collaborating with the customers to provide high-quality products in the right time. Lastly, we are going to make an early investment within this year for the research and the development of microdisplay. I will let you know all this in detail. As you may know, the display industry is a huge business, right? So we must focus on meaningful technology in a business context. Which technology looks important? Which one looks less significant? We need to consider and carefully decide whether we can secure proper level of scale and profitability. A decision of a panel maker may lead the future of research and ecosystem. So today, I'm going to explain that kind of innovation technologies. They are the result of Samsung's careful deliberation. Most premium smartphones now take OLED. You can easily find OLED panel on budget model too. And now, consumers are pretty friendly to OLED screen. That's why Samsung is exploring new value for customer. Yesterday, VESA announced a new standard called Clear MR. It is the first index for quantifying motion blur. It integrates scan rate and also eye tracking and response rate. This index will clearly demonstrate OLED is visually superior to LCD, especially in dynamic video contents, such as sports, film, and game. On top of this, we are also developing on-cell film technology to handle high luminance HDR over 2000 nit. And we adopted under-panel camera for full screen. Our OLED also introduced 12-bit color depths, like these. Samsung display carries on game-changing challenge. In 2010, so we developed integrated touch display. Since then, we have continuously innovated our technology and also developed a high-performance organic photodiode. Thanks to this innovation and development, we will soon commercialize the fingerprint sensor available on the entire screen, not just at one spot. This means the security level will increase dramatically, and it will lead the development of diverse applications. In addition, all-in-one sensor technologies have become crucial. That sensor will integrate 5G antenna, biosensors, and many others. I believe related research area will be widened, including smart algorithm and noise minimization technique. This way, future OLED will evolve into a panel with various sensors and will create new value. In 2007, Samsung Display opened the era of OLED based on our exclusive evaporation technology. Now, so we are making another breakthrough by taking new evaporation method on single mother glass. The Gen 8 production is designed to speed up OLED replacement in the notebook market. Combined with large-size foldable panels and touch integrated technology, I believe we can maximize the synergy effect. Yes, of course. With this new production line, we will be targeting automotive market as well. The auto industry is redesigning a car and also user experience. In this new concept, all the surface in car will be covered with display. Now, lots of car makers have requested collaboration with the Samsung Display. You will see what will happen in the automotive. Then, what kind of customer value auto display can deliver? First, most important thing is safety. It's very critical value of vehicle. Drivers every time need assistance to deal with dangerous situation. So, our OLED adopted the true black and fast response time to help drivers see objects even in the dark. Also, Samsung OLED adopted the privacy mode. With the help of this mode, even when a passenger plays video on the next seat, drivers can focus just on driving. Interior design also matters, as it increases the value of future car. And also narrow bezel provides more area, even in smaller display. And combining all of these, the multi-lamination tech enables the pillar-to-pillar design. In the car, entertainment is evolving as well. Samsung OLED adopted the tandem structure to enhance its brightness and reliability. Are you excited to see how Samsung will make the future car with all these imaginative displays? Have you seen the product with the various form factors here in the IMID exhibition? As you may have seen, the foldable products are just the beginning of the form factor transformation. Going forward, Samsung Display plans to offer unforgettable devices like multi-foldable, slidable, and even stretchable to prepare for diverse applications and user cases. We are developing differentiated technologies like stress-free panel. Next, QD OLED. When you look at the quantum dot OLED, you would feel it is much brighter than the other displays with the same luminance level. The existing luminance standard didn't reflect the exact brightness of display. That's why we developed XCR, U standard. It's integrated experienced brightness standard. We tried to assure the outstanding image quality of QD OLED. The XCR quantify the actual brightness by combining luminance and also color gamut to be more specific. So when comparing QD OLED with white OLED, under the same peak white, QD OLED is about 40% brighter than white OLED. Also, QD OLED covers 90% of BT2020 color space, unbelievable. And it outperforms the coverage of white OLED. Moreover, QD OLED solved lifespan problem by enhancing its reliability. Then what's next? Light emitting structure and new materials will lead the next XCR innovation. We are also focusing on inkjet patterning technology to spur innovation, to accelerate innovation in productivity and also resolution. QD OLED display achieved remarkable yield in 6 months since we began mass production. That's the reason why I made is a QD ramen. Have you guys have that? I will give you all you guys. So, it's fair to say QD OLED is on a smooth track and ready to present richer visual amusement to users. Have you seen the Squid Game? It's on Netflix, right? Well known for the actors wearing red and green uniform. You know, QD OLED can express those colors the best ever. With the QD OLED screen, you may have entirely new visual experience. Samsung got lots of awards recently. Here are a couple of. EcoScale OLED won Display of the Year at the SID 2022. And also QD OLED got King of 4K TV last month. For the next years to come, we expect to create another milestones with outstanding products. Let's take a moment to talk about small micro display, from TV to small one. The importance of a near-eye device has increased to maximize the lifetime experience in the metaverse. The market is still debating whether to go for AR, VR, MR, XR, and lots of alphabets with R. However, one thing clear is when the market will kick off. Nobody knows, but if we provide definite customer value through technological solution, it's possible. For the development of microdisplay, we need to expand light source from organic to inorganic material. And backplane substrate from glass to vapor, maybe. In other words, there will be whole paradigm shift where display evolves into semiconductor. It will create total change in the entire value chain. Also, cross-industry collaboration is strongly required between display, semiconductor, physics, and even optics. Lots of changes will come. Are you ready to make them? Especially student, you will be having your vision with the new area of microdisplay, not me. It's because I'm too much old to enjoy the bloom of microdisplay, right? AR and VR devices are a chance for display industry to expand value chain and converse with other industry. Samsung also has prepared for microdisplay with a very positive outlook. And we are considering the possibility to expand our business. For example, XR module, including waveguide, will create value added and synergy. Samsung Display will do whatever to meet various market needs. But still, we have to overcome lots of technical challenges before us. For smooth development of microdisplay, the efficiency of LED material and waveguide solution need also improvement. Just considering the market demands and technical readiness, some products will be available for initial mass production in 2024. We strongly expect the commercialization of microdisplay around 2026. Collaboration with industry partners is getting more important than ever. So far, I have mentioned the era of self-luminous display, and also our strengths in OLED and QD, and also future display like micro one. In the last couple of slides, I'm going to share yet another elements that will drive quantum leap of display industry. First one is diamond pixel, you guys may have seen, and also EcoScale OLED Plus, and Samsung Super Driving Range, SSDR. All these are Samsung Display's representative patents on OLED. I believe it's difficult to create premium OLED without all these powerful IPs. And such accumulated IPs empower Samsung Display to have unrivaled OLED heritage. Samsung Display applies for numerous patents every year based on continuous research and development. You know, our patent quality, 7th highest in the world. And in Korea, the highest, even better than Samsung Electronics. Other than just having strong IPs, we are looking for the opportunity how IPs can practically contribute to our business. Next is ESG, a global hot topic you may know. Here is one of the most beautiful, famous beach during summer. Why? It's because of white sand and also beautiful coastline. Did you know sand needs to be replenished to maintain such a beautiful beach? Tens of millions of dollars are spent on coastal maintenance for many years. That caused by climate change and subsequent erosion. You know, glass is wholly made from sand. Samsung Display has been recycling waste glass since 2016, and the amount of recycled glass is as much as to cover the entire Haeundae Beach. I named this cycle the Journey of Sand. You are seeing the dolphin. It's like in drama, weird Otoni. You know? Nobody knows? Woo-young-woo. We must save that dolphin. Like this, we need joint effort to guide every resource to make its own journey. Under the slogan of Planet First, Samsung Display has made an ESG system. This manages product life cycle from design to disposal. What's most essential is to create eco-friendly product from the design stage. We need to enhance product sustainability by making products energy efficient, resource saving, and human friendly. For example, EcoScale OLED Plus reduced power consumption by half compared to conventional OLED. Under fabrication, reducing greenhouse gas and replacing it with ESG gas is important. And more technological solutions are needed. We also help customers to use our products longer than in a greener way. Adaptive frequency and True Black are some of our solutions for a longer battery lifetime. Lastly, Samsung Display received platinum level certification in the zero waste to landfill category. Since these efforts are in the beginning stage, I'd like to ask for various research and ideas from academia, also here in IMD, like some session for ESG. So nowadays, digital transformation is taking place in all industries, but it's not a new concept for the display because we launch large-scale manufacturing factory. However, it's crucial to upgrade automation level and reduce human error. Samsung Display currently operates level 2 static digital twin with real-time monitoring based on digital data. And we are in the process toward level 3, dynamic digital twin. This is all based on prediction-based one. In the near future, before my retirement, maybe, we plan to realize fully automated fabrication. That's level 5. That will enable two-way control in real time. You will see Samsung's dream display factory with 100% automation and yield. Today, I have touched disruptive innovations of display industry. And also, I look forward to enjoying this journey with you together. Next generation OLED will create new momentum for quantum leap in the display industry. Samsung Display will not only produce high-quality products, but also play a leading role as a total solution provider. Here in IMD 2022, I really hope this moment will mark a meaningful start. At this time of turning point, collaboration between academia and business sector would be a key to open this kind of opportunity. Thank you. Grazie. 감사합니다.
Thank you for great, actually, the keynote speak from Dr. J.S. Choi, and President and CEO of Samsung Display. Keynote session, unfortunately, we don't have no question and answer. And please to show round of you big applause. Thanks again for keynote speaking. So let me introduce the second, our keynote speaker, Professor Stefan and Forrest. So, before start of his talk, let me briefly introduce his autobiography. And he got his PhD degree in physics, University of Michigan, year 1979, and then actually Professor Steve Forrest to join USC and moved to Princeton University in 1992. In 26, he rejoined the University of Michigan as vice president for the research, where he is Peter A. Franklin Distinguished Professor, University Professor. He is also fellow of APS and IEEE and ISA, also the member of National Academy of Engineering and the National Academy of Science, the American Academy of Art and Science, and also the National Academy of Innovator. Very long. I take a break now. Okay. Also, he published a lot of actually really interesting paper and also a lot of award, but I cannot introduce all of them due to the time limitation. Okay. So today's he's going to talk about progress in achieving long lifetime and high efficiency from the blue. So please show your big welcome to Professor Forrest.
Thank you very much. It is such a delight to be able to come back to Korea, a place that I have been coming back and forth to for probably 30 years now. And I thank the committee and the organizers of this conference for inviting me. I also want to thank Dr. Cho for the previous talk, because it really sets the stage for what's in front of us with OLEDs. And I think for young people and for researchers in the field, we feel perhaps from such a talk that it's a very mature technology and there's nothing left to do. Of course, Dr. Cho and I both agree that that's not the case, that there are as many questions in front of us as there are behind us, and there's none bigger and more important, in my view, than long-lived phosphorescent blue OLEDs. And that's what I'm going to talk about today. So I'm going to go from the general, which you have just seen, and talk about something a little bit more specific. Now, I have a fairly long background in semiconductors, and of course, organic semiconductors get a bit of a bad name because it seems that everybody thinks they don't last long. And I think we have to, as a community, dispel that myth. And I just show a few of these probably very outdated numbers, but nevertheless characteristic to show that organics can live a very long time. As a matter of fact, we do photovoltaic research with organics that last even thousands of years, extrapolated lifetime. But there's a weak spot in our world, and that is in deep blue phosphorescent materials and devices. And that's what I think is what I would class as the most high-value problem today in all of the field of organic electronics, and also the most difficult to solve. There's a lot of people out there who are working on this from many different angles. So let me just set the stage by reminding us what's going on. It's very difficult to say that reds live longer than greens, that live longer than blues, because these are all optimized materials for different applications. But I think in general we can say that red OLEDs live longer than green, live longer than blue. So that immediately suggests that there's an energy problem involved. If you look at the wavelength of light and the energies, we go from 2 volts for red light to 3 volts for blue. But again, if you look at the molecules as just one of many molecules that would exist in an OLED, carbon-nitrogen bonds, for example, carbon-carbon bonds, with the exception of a few bonds, the bond energies are well above anything here and would suggest that everything should be stable. So there doesn't seem to be enough energy to really damage any of these molecules that we use. We don't typically use molecules that have these weak bonds like oxygen bonds and so on. So is there enough energy? Well, I'm going to take you back on a little bit of a history tour. Our first blue phosphorescent OLED was demonstrated in the year 2000 at Princeton, and by 2008 a lot of people had gotten into the field and were working on making more and more stable molecules, and blue was evasive. And we knew that there were a lot of smart chemists out there. I work with one of the smartest in the world named Mark Thompson, and nothing that we did and other people at Samsung and so on did was really improving the lifetime of blue. So we took a step back. I'm a physicist, not a chemist, and we thought maybe there's a physical process as well. I mean, there's no question that the chemistry has to be there, that the molecules have to be robust, but nothing seemed to be working there, so there may be a physical origin. So my student, Chris Giebing, came up with a purely physical model, that you have a host and you have your dopant, and after a while something bad happens when you run the device and you get a defect state. And we know that defect states create non-radiative centers, so that would eventually account for the loss in light. We had no reason or understanding of what that defect was due to, but nevertheless, that was the starting point. And where does all the energy come from? And I'll just show this briefly. It's what's called a Jablonski diagram. You can think of having a triplet state over here, and it collides with a triplet in an adjacent molecule. It gives up its energy in a non-radiative way and promotes this triplet up to some higher energy state, and then the molecule, this is a dissociative state. The molecule basically falls apart. This is called triplet-triplet annihilation, and everybody in the field is aware of this. And now we're talking not about 3 volts, we're talking about 6 volts. There's enough energy there to do the destructive process that we're all worried about. And you can also do this with a charge. If the exciton collides with a charge known as a polaron in organics, that too will give you about 6 volts. So there's a real probability here that we've got a problem that's very fundamental, because you can't get rid of this, particularly at high brightness. So that was physics. We then turn to this is a very slow motion history I'm talking about, because that was 2008, and now we're talking about 2019. We're now saying, what is the chemical origin of this defect that we seem to be seeing all the time? So we did something very simple. We built an OLED device, and with the most stable blue that we had at the time. This was actually came out of Universal Display Corporation, DMP. We love it dearly. It is, however, a slight bit green, not deep blue. Nevertheless, we ran this thing very hard, and then we looked at what the products were, what had shattered in the device. To do that, we did mass spectrometry, and you can see here that the unaged material looks something like this, and then you get some new peaks when you run it really hard for a while. A detail is, would you create ligand loss? Would these ligands just cleave off, or would they actually fracture? And just from analyzing of the data, you can find out that ligand loss is the biggest problem. These are various species that we found in our mass spectrometry of the aged device. So these are dopant defect number 1, et cetera. Okay, so that gets us to the fact that these molecules are degrading, but would that cause a defect that would be non-radiative, that would reduce the luminance within the device with time? And working again with our friend Mark Thompson, we did density functional calculations of all of the products that came off from this molecular destruction. And this gray band here is the LUMO of the host. That's where the electrons come in the device, and the HOMO of the dopant, the iridium. It conducts the holes. And you can see that most of the time, these products are sitting in pretty benign areas. If it has a wider energy gap, then here nothing's going to happen. But there are a few host and dopant fragments that have defect levels right where you don't want them, and that was the source of the loss of luminance. Okay, so now we've traced it. The molecules, though very strong from a chemistry point of view, that is a bond energy point of view, we're still fragmenting because of this triplet polaron annihilation, which we implicated the most strongly. So how do we solve the problem? That's just the source of the problem. Now we we have a model, we have good chemistry sets, et cetera, but what do we do to solve it? And that's, of course, what we're all interested in. And basically, what you have to do is you have to reduce the triplet density. Now, you're running the device quite bright, so there's lots of triplets, and they're banging up against each other, and they're fragmenting. It's actually only 1 in a billion triplet collisions or annihilation events that actually ends up in fragmenting a molecule, but turns out you go through a billion triplets rather quickly when you run an OLED. But if you reduce the density of the triplets within the emission layer, you can then hopefully get to longer lifetimes. And believe me, the community has tried everything, And I'll talk about those steps to reduce the triplet density. They don't always, the papers that you read might not say that, but that's what they're doing. From the Giebink model, the probability for creating molecular destruction is basically proportional to the rate at which molecules fragment. That's 1 in a billion, let's say, divided by the radiative rate of the molecule. Now, for triplet emitters or triplet controlled emitters, TADF molecules and iridium complexes and so on, this tends to be the inverse of about several microseconds. Now you can make a cavity, and I'll talk about that later, in which you give that promotes a faster decay of the triplet state. The faster the triplets decay, the lower their density is going to be. You want them to emit light right away. Okay, that's called the Purcell factor. We'll get back to that later. So you can enlarge the recombination zone. Of course, you can increase outcoupling efficiency and make the devices more efficient. All those things work, but the key is you got to get the exciton density down. So let's take one step back and look at our molecules. It turns out that our first really convincing phosphorescent device for the industry was a device in the green using iridium PPY. And this is the emission decay time for all of these various molecules as put together by Yersin. And you can see the platinums are a little slower and the iridiums are pretty fast, but iridium PPY is about the fastest. And everything bottoms out at 1 microsecond. What we have in the bottom is what's called the zero field splitting energy, and that you can see over here. The triplet state has, per its name, 3 substates, and they're sitting at E1, E2, and E3, and the energy difference between all those states is called the zero field splitting energy. The problem is that as this gets small, the triplet that starts out here gets energetically pushed up here by temperature, and then it emits. So it takes more and more time in the triplet state. So you want that to be as small as possible. But the question is how short can I make a heavy metal molecule emit? And the answer is always going to be 1 microsecond. That's it, okay? So what about TADF molecules? They're all the rage these days. And you ask the same question, and basically they're a little slower in general, but the best you can do seems to be around 1 microsecond. Or is it, I'll show you some TADF molecules that are actually faster than 1 microsecond. But we come to the same solution. Just a very quick, brief look into the world of kinetics. In a triplet emitter, as I said, this is the zero field splitting. The problem is that if you start off here, the lowest state, it will be thermally excited into higher sublevels of the triplet, and that takes time, and so it comes down. So the actual phosphorescence lifetime is the time for the lifetime of this emission times the equilibrium constant, how many of the triplets actually make it up into there. With TADF, same story. Here you're trying to go from the triplets, you always push it into the singlets because you want singlet emission, but if they're sitting in the triplet manifold for a long time, they're hanging around there waiting to die. So again, TADF is equal to the singlet lifetime, which is very short, but times the equilibrium constant, how many states actually sit in the triplet versus the singlet. They're all sitting in the triplet. So you come to the same conclusion. These are the types of TADF molecules that people are looking at. The way TADF depends on making the triplet to singlet energy, the exchange energy splitting, to be as small as possible. And the way that Adachi first came up with this, was to make the acceptor group and the donor groups perpendicular to each other. So there was very little overlap between the electron and hole, basically, or the excited state in the molecule. So they didn't communicate very well, and that brought the singlet-triplet splitting as small as possible. Mark Thompson has taken a different approach to this. He uses a metal linker. These are not phosphors. He just uses a metal linker where he has the donor and acceptor states now coplanar, but he changes the distance between them by the metal linker. And you can see over here the sort of distances between, well, in this case, the carbon and the nitrogen and the metal. And he uses copper, silver, and gold, which are coinage metals, right? Those are the metals that are in your pocket. Well, they're kind of in your pocket. You got a lot of zinc in there too and stuff. The governments cheat us, but nevertheless, it's mostly copper, silver, and gold. And you can see you can change those distances. Now, why am I talking about this? Well, first of all, these are just showing copper complexes. So they're up at 20% without any outcoupling help. And they look, you can go from the deep blue to the very deep red with these molecules just by changing, as usual, the ligand structure. So they look good. But the important thing is that now we can get down to 0.5 microseconds. We got below that dashed line with TADF molecules using these metal organic compounds. And you can see you can, whoops, going back, I guess you go back that way. You can see you can go from the deep blue and also out to the red. It just doesn't show it here. So we're getting down to 0.5 microseconds. I think he's even getting better numbers than that today. Unfortunately, these molecules are not as robust as we'd like them to be. So then you bring in another problem, which you're back to chemistry. How do you make them really robust? So that's the chemistry approach. We can see we're hitting some real fundamental bottom lines here. You're only going to get this so fast. Any TADF molecules, although you get singlet emission, the time is controlled by the triplet. So they're basically triplet emitters as well. So one of the ways you can spread out or you can reduce the exciton density is to spread it out in the EML. And this just shows a conventional device where you have your dopant. We're going to consider this to be an iridium dopant, and a host, let's say MCVP. This is the whole transport layer. This is the electron transport layer. Turns out that the host conducts electrons far less efficiently than the dopant conducts holes. So you get all your excitons piling up at one end. So my student Yifan Shang took, again, this very nice molecule, DMP, and he graded it backwards so that the holes have more and more trouble making it all the way to the ETL interface, and the electrons have a lot more molecules here so they can penetrate deeper in, and that spread out the exciton density. Does that work? It actually works better than anything that we've yet really seen in the literature, even though this is pretty old. Now, I know that within industrial labs and so on, that people are doing other things that they're not always talking about. But this tended to be quite a good result. This was a conventional device. Then we grade it, and we get now to 300 hours to T80. And if we stacked, which is another way of spreading out the emission layer by stacking multiple devices in tandem. This is a double stack device. We're getting out to 600 and some odd hours. So this is obviously an improvement, and it's really based on this model of triplet polaron annihilation. So that's one way we can do it. Then we thought, well, maybe the best way to do this is to really just get rid of those extra triplets. So we put in a third molecule in the emission zone, which we call the manager molecule. And so over here we can see some triplet excited states. What is the history of those triplet excited states? Well, the best thing that could happen is it just emits. We love that, and that can be 100% internal quantum efficiency. But once in a while, we get triplet annihilation, and let's see. One goes down and one goes up. The one that goes down, this is non-radiative, so no lights come out yet. And then the one that's up high, well, the good news is it can come right back down and then emit. I'm down to 50% quantum efficiency in that reaction, but at least nothing bad has happened. Unfortunately, 1 in a billion times, this happens, and the molecule flies apart. So now we'll put in a manager molecule, and we'll take that doubly excited state, and we'll let it go over to the manager, and then emit. I'm down to 50%, but I kept it from going, the initial molecule from going into a dissociative state. That would be good. That was the plan. But the manager molecule can also dissociate. Okay, so it's not in the emitting path, but nevertheless, it can die as well, which means that with time, you won't have the manager molecule around. So the requirements are that it has to be, the manager has to be at an energy intermediate between these two states. It has to be stable, and fast energy transfer has to occur from the emitting molecule over to the manager. This is a detail I won't go through, but I think the bottom line is that in placing the manager at various regions within the device at LT90, this was work of Jae-Sung Lee, who's now at SNU here in Korea. We got 5 times the lifetime of a conventional device and 3 times the lifetime of a graded device. At T80, that advantage disappeared a little bit because we were chewing up more and more of the manager molecules. But if you put this all in a device, you grade it and you manage it and so on and so forth, and you make a nice deep stack of multi-junction OLED. I think this is 5 stacks deep. It can actually function quite well. So T70 is what we want to do for lighting, not for displays. We get to 80,000 hours at 1,000 nits, at 3,000 nits, 15,000 hours. So these technologies are helpful for displays, for lighting, but unfortunately for displays, you have to have a much deeper blue, which means you have a much higher photon energy, which means destruction is even more rapid. So what more can we do? So one of the things is can you use rapid transfer to the singlet state? So back in the year 2000, my student Mark Baldo demonstrated what we called phosphorus-sensitized fluorescence. Maybe this is a key now to lifetime. What happens in phosphorus-sensitized fluorescence, this is another energy level or Jablonski diagram. On the host, you create 1 singlet and 3 triplets, statistically. We then put in a phosphorescent molecule here, and the singlet goes over to the singlet of the phosphorescent molecule, and then by intersystem crossing, it ends up at the triplet. The triplet just transfers directly. And then with very low doping, we put in a fluorescent molecule, and the triplets, because this is a radiative material, can now Forster transfer over to the singlet state. You get 100% of all the excited states going over the singlet. You haven't lost any efficiency, and boom, you get your light out. The total time of this now is determined by the rate of intersystem crossing, which is about a nanosecond, and the rate of fluorescence, which is about a nanosecond on order. So this whole thing really brings the lifetime down. This is absolutely brilliant way to increase the lifetime of phosphorescent molecules. What about TADS? Well, there's a problem. So with TADF molecules, the singlets are formed on what's called the sensitizer T. This is what I call or TADF sensitized fluorescence. It's very similar in principle to phosphor-sensitized fluorescence, but it has a name all by itself called hyperfluorescence. And the singlets, so the singlets now transfer over to the fluorophore, and you get light out. Unfortunately, the time of this process is limited by the time it takes the triplets to get over to the singlet in the TADF sensitizer. I think it's called the assistant molecule. And that turns out to be a couple microseconds again. So this is not going to help you increase the lifetime in principle for TADF, but it should do a miracle on phosphorescence sensitizers, on phosphor-sensitized fluorescence. There has been a demonstration of this by Heimel. And what you really need is you need to have a donor molecule, the iridium complex. It has to be in the blue with a very small Stokes shift. And here you can see it. It's a little bit on the greenish side. And you can see the lifetime has decreased quite well. Actually, the lifetime has decreased from a fully phosphorescent device of 1.6 microseconds to about 0.5 microseconds, about a factor of 3. Unfortunately, the lifetime only improves by a factor of approximately 2. There's a factor of 2 here that is just hanging up on everything we do. We can't seem to do a whole lot better. The managed devices did significantly better, but only briefly, and they're kind of complicated. So this is a demonstration, but obviously, for one reason or another, it's not nearly the lifetime that you would expect for phosphor-sensitized fluorescence. So what else have we got left? And this is the last thing I'll talk about. Using cavities. A OLED is a weak microcavity device. So what about using the cavity to increase the radiative rate? Now, because I'm a physicist, the one thing I love about physics is there's some really simple quantum mechanical rules, and Fermi's golden rule every undergraduate knows about. So the radiative lifetime is just equal to basically the optical field intensity squared times the photon density of states. How many states are available for these emissions? And one way you can increase the photon density of states is to couple to what are called surface plasmons in the cathode. A surface plasmon is basically if you have a radiative molecule that's near a metal, that light that goes into the metal creates a separation of charge, which is a traveling wave. It's quite lossy, but nevertheless, it now avails a higher density of states for emission. And this was done by the people at Universal Display Corporation. They did it in the green. Of course, green lasts forever, but it's still a nice demonstration. They used, for the surface plasmon coupling, silver nanoparticles on top of a silver cathode. And you can see that, we're back to that factor of 2. This is standard OLED, basically. And then the one with the surface plasmon this is the radiative lifetime. So the radiative lifetime has gone down by a factor of 2, which means the rate has gone up by a factor of 2 because it has a cavity with a Purcell factor, which is basically the coupling or the strength of the cavity, which is a factor of 2. Okay? So we would expect, according to Giebink theory, that this factor of 2 increase in radiative rate should result in a decrease in the rate of defect formation by a factor of 2. I think everybody's getting that point, which means that the lifetime should double. And guess what? The lifetime doubles. In this particular cavity device, it came with a price. Doesn't necessarily have to. It depends on how you design your cavity. But it comes at a price of decreasing the output coupling, so the external quantum efficiency has gone down. Also, let's say roughly by a factor of 2. That's a penalty here, but it doesn't need to be. Remember that's surface plasmons, because metal is resistive and you're creating a eddy current within the metal that can create that loss that we see. But like I said, this is a nice demonstration that shows that if you decrease the lifetime, the radiative lifetime, you increase the operational lifetime. So this is work that we're doing in our lab. Different types of cavities. They don't use nanoparticles, but I just wanted to show you this is wavelength versus what's called the in-plane K value, or the propagation constant within the OLED plane, and anything less than 1 is stuff that you see. So those are air modes. Of course, there's glass modes. You can't quite see them here, but there are quite a lot of them. And then there's waveguide modes that are just propagating in plane. All of this you can't see, but they're okay, because you can, with a few optical engineering tricks, you can get them all out and push them into air modes. But these are the surface plasmon modes. See, they're really bright. That means a tremendous amount of energy is going into surface plasmons in this cavity. And here you can see, depending on where you put the emitting molecule in the EML relative to the cathode, we can get per cell factors of on the order of 4 or 5 and still have an output coupling efficiency of 20 to 25%, assuming that the molecule is 100% efficient. And when you do that, you actually get pretty good results. This is just for different cavity devices, but here you can see, here's just a typical EML with ERDMP. This is the radiative lifetime, and then you put them in these cavities, and the rate goes up by, well, about a factor of 2. And the lifetime goes up by about the same amount, okay? It goes up by, this is the operational lifetime. So what I've shown you is a very, very complicated problem with a narrower and narrower pathway to success. But there's a lot of good things happening, and I have a lot of confidence. We're really right on the edge of making phosphorescent devices or triplet emitting devices with sufficient lifetime for the deep blue. And I haven't shown you everything that's going on in the field, but there's a lot, both in our lab and in others, that are making real progress. So the pathway to long lifetime blue emitters is controlled by the triplet lifetime, which is both phosphors and TADF molecules. It remains long, but the path is pretty narrow. Those are all of the various strategies one can use. So what are those strategies? Well, better life through chemistry. Every layer in the OLED matters. It is hard in the blue to create good blocking layers because you're up near the vacuum level. And so the materials become quite unstable to reduction sitting up there. But we have a reasonable material set that we can use there. And of course, all of those various layers, including and especially the emission zone, all the molecules have to be very, very robust with strong bonds. We have to lower the exciton density of emission zones. That's really the only theme of this talk. Shorter radiative lifetimes is one of getting a lower density of excitons. Get the energy out of there quickly. Improved outcoupling. I didn't talk about that, but an OLED is a real gold mine for optical engineering and for coming up with strategies to get the light out. There's some people I know in this audience who have done really marvelous work in getting up to 80% external quantum efficiency by optical engineering. These are very important strategies because they put less pressure on the EML to generate so much light. So improved outcoupling, shorter radiative lifetimes I talked about, and coupling to plasmons. Solving this problem, as I said at the beginning, is likely the single most important challenge confronting the entire field of organic electronics today, and specifically, of course, OLED displays, which is the concern of this audience. Blue full LED lifetimes are suitable for lighting today, which is great, but they have to compete against indium gallium nitride, which is a tough act to follow. But there's a lot of applications and attributes of OLED lighting that LEDs can't match. And so there is a market out there, but it is not going to be anywhere close to what we get with displays. We can use lighter blues and fewer photons per segment required than in displays. And there are lots of other challenges lurking as well. This is a great field. It has sustained my research now for a few decades, and many of you the same. There are many challenges ahead. There are as many, if not more, challenges ahead as there are behind us. So with that, I want to thank my students. You can kind of tell when this picture was taken. That's how they look in real life. And we were probably in violation of all kinds of university rules when we took this. And the arrows are pointing out the people who are responsible for some of the work in this that I presented, but a lot of them have gone off to productive lives in the display industry as well as in university. So I really am indebted to my students, and of course, I'm very deeply indebted to the Thompson Group, Mark Thompson and all of his students at USC. The work has been supported by the US Department of Energy, who's concerned with lighting, not displays. But we can use that learning from lighting and transfer it to displays, and of course UDC. So thank you very much.
Okay, thanks again for a nice, actually great and keynote talk, Professor Stefan Forrester. And let's move to the third keynote talk, and Dr. Tomoyuki Mishina. Unfortunately, due to COVID-19, he will give a talk in a live, actually, the online Zoom connection. Okay, before start his talk, and let me briefly introduce his autobiography. And Dr. Tomoyuki Mishina received a PhD degree from Tokyo Institute of Technology in year 2007. And then actually he joined to Japan Broadcast Corporation, NHK, Tokyo. And since 1992, he has been engaging in research on three-dimensional imaging system in the Science and Technology Research Laboratory, NHK. Dr. Mishina?
Yes.
Can you hear me?
Yes.
Okay. Okay.
Yes. Thank you very much. Good afternoon. I am Tomoyuki Mishina from Japan Broadcasting Corporation, Science and Technology Research Laboratories, or NHK STRL. Japan Broadcasting Corporation is named NHK in Japan. First, I would like to correct my position as it changed to senior expert in July of this year. I am honored to be invited here as a keynote speaker of IMID 2022. NHK STRL held an open house in May this year. The title of my talk, Cutting Edge Technologies to Spin Up Future Media, is the theme of the open house. Today, I will introduce these display technologies exhibited at the open house. In the future, the increasing spread of high-speed, high-capacity networks is expected to permeate societies with lifestyle assistance services enabled by advanced IoT technology and artificial intelligence. What consequences will these trends have for the future of broadcast media? NHK SDRL, the research arm of the public service media NHK, in participation of the media environment in 2030 to 2040, has developed Future Vision 2030 to 2040 to identify objectives and directions to pursue. I will introduce the projected media environment around 2030 to 2040 at all time in all spaces and venues, indoors, outdoors, and even while driving. Viewers will be able to use devices of their choice to enjoy immersive content. The same content can offer distinct experiences depending on the delivery medium. Images and sound via large screen televisions, 3D-dimensional shapes and textures for scenes via 3D TV, and immersive sensations provided by wearable displays. AR technologies will enable viewing spaces to be shared with others in distant locations, leading to new viewing experiences that facilitate personal interconnections through shared content. NHK SDRL has identified 3 key R&D focal points that are necessary to achieve our future vision to provide new user experiences. Immersive media offers more realistic real-world experiences beyond anything provided by television. Universal services are technologies that deliver any content, anytime, anywhere to anyone. Frontier science features cutting-edge scientific research for both future media creation and sustainable society. Here, I will mainly introduce the elemental technologies related to the display area that NHK SDRL is currently researching and developing. I will introduce our research into the space sharing content viewing system, which we are developing using AR technologies where viewing spaces and content can be experienced together across distant locations. In the space sharing content viewing system, 3D images of people in different places are composed as video content and displayed live-size on the head-mounted display, HMD. The 3D image of each user is captured in real time with a depth camera and transmitted by the network to the other user. The user can share space with another user while watching the same content and communicating by voice and gestures. Please look at the explanation video of space sharing content viewing system. The explanation is in Japanese, but the caption is in English. So please read the captions.
空間共有コンテンツ視聴システムは、遠く離れた家族や友人と空間を共有しながら一緒にコンテンツを体験できるシステムです。この展示では壁の左右を離れた場所に見立てています。ユーザーはヘッドマウントディスプレイをかけてコンテンツを体験します。体験者はこの距離センサー付きカメラで3次元映像として撮影され、その様子が向こう側にいる相手のヘッドマウントディスプレイに表示されます。 離れた場所にいるユーザーの3次元映像は距離センサー付きのカメラでリアルタイムに撮影され、ポイントクラウド形式により通信経由で伝送されます。同様に自分の姿も3次元映像で相手のユーザーに伝送され合成表示されるため、お互いに会話や身振り手振りといったコミュニケーションを取ることもできます。
見える？見えてます。
さらにこのヘッドマウントディスプレイにはステレオカメラがついており、外の様子を見ることができるようになっています。ステレオカメラを用いることで VR 映像を共有している時でも現実空間の自分の周囲を表示することや、お互いの部屋に AR 合成される出演者の3次元映像を一緒に楽しむこともできます。
Through the development of this system, we are pursuing research on experiences that encourage deeper connections with others through content. I will introduce our research into a portable interactive 3D display that we are working on to develop a handheld device that can display 3D images. When 3D video is used in broadcasting, it is important that natural 3D images can be seen without special glasses. Hence, we are conducting research on integral 3D, which is classified as a light field display. The basic principle is integral photography, published more than 100 years ago. A 3D technology reconstructs optical images by capturing and displaying light rays reflected from objects using a lens array of microlenses for both capture and display. The figure on the right shows the reconstruction of optical 3D images by reproducing light rays from the elementary images using a lens array. The optical images can be observed without special glasses and change smoothly according to the viewing position. Here is a movie showing how an integral 3D image changes according to the viewing position. Even if the viewer moves in the horizontal or vertical directions, the 3D image changes smoothly according to the viewing position. We have developed a portable interactive 3D display system using the integral 3D technique. The 3D display device acquires the viewer's viewing position and device operation, and the server generates elementary images based on this information. This enables the viewer to view 3D images according to the viewing position and the operation of the device. Please look at the explanation video of portable interactive 3D display.
このディスプレイシステムは携帯端末、サーバー、ルーターで構成されます。携帯端末で視聴者の視点位置情報や操作の情報を取得し、サーバーでそれらの情報に応じた要素画像を生成します。これにより視聴者は見る位置や操作に応じた3次元映像を見ることができます。処理フローの詳細についてご説明します。こちらが処理フローの全体図です。まず視聴者の顔を携帯端末のカメラで撮影し、機械学習を用いてその画像における顔パーツの二次元座標位置を推定します。そして顔パーツの二次元座標位置と操作情報をサーバーに送ります。サーバーではその二次元座標上の顔パーツと平均的な3次元の顔モデルを使って3次元座標化し、3次元空間での視点位置を算出します。
そしてその視点位置と操作の情報に応じた要素画像を生成します。生成された要素画像をエンコードし、携帯端末に送ります。携帯端末では画像をデコードしてディスプレイに表示します。これで視聴者は3次元映像を見ることができます。視点位置や操作の情報に応じてこの処理フローを実行することでインタラクティブな3次元映像表示を実現しています。
This is the developed 3D display and its specifications. Using Intel 3D display technology that tracks the viewer's eyes, we expanded the horizontal viewing zone by approximately 4.5 times and the vertical viewing zone by approximately 5 times the conventional viewing zone without eye tracking. As a result, the viewing zone angles were 91 degrees horizontally and 49 degrees vertically. Using a small display with a pixel density of 807 ppi and a lens array with a long focal length of 1.2 millimeters, we doubled the light density of reproducing 3D images in both the horizontal and vertical directions and improved the image quality. I will introduce our research into the light field head-mounted display, which we are working toward viewers experiencing 360 degrees content with immersive feelings and a sense of reality. With the progress of AR/VR technology, we expect the usage of head-mounted displays to increase in the future as a viewing device along with TVs and smartphones. We developed a head-mounted display, HMD, that enables viewers to view natural 3D images. Light field technology makes it possible for real-world reproduction of the light reaching the eye from an object. In this light field HMD, a lens array is placed in front of the display, and the elemental images corresponding to each lens are displayed. Here, by forming the 3D image as a virtual image outside the display, we reduce the distance between the lens array and eyepiece and make it approximately the same size as the conventional HMD. Please look at the explanation video of light field head-mounted display.
ライトフィールドヘッドマウントディスプレイはディスプレイと2種類のレンズであるレンズアレイ、接眼レンズで構成されています。ディスプレイには要素画像という特殊な映像を表示します。これは3次元映像を作る光線の色や輝度の情報が含まれています。レンズアレイは微小レンズが2次元上に並んだ光学素子です。ここから3次元映像を形成する仕組みについて説明します。ディスプレイの画素から出た光線はレンズアレイを通過後、ある位置で交差した後、接眼レンズで屈折されて目に届きます。接眼レンズで屈折された光線を逆方向にたどっていくと、異なる奥行きに存在する2つの点からの光線を再現していることが分かります。 目に届いた光線は目の水晶体で屈折されて網膜に届くので、焦点を合わせた点が鮮明になり、もう一方はぼやけて見えます。このように奥行きの異なる点によって3次元映像が構成されているので、実世界と同じように焦点を合わせることができます。理研ではライトフィールド HMD の実現に向けて HMD 本体の薄型化に向けた研究開発を行っています。従来はディスプレイの画素から出射したいくつかの光線をレンズアレイ通過後、ある位置で交差させた後に接眼レンズで屈折させていました。今回図のように光線を交差させずに接眼レンズで屈折させて、従来と等価な光線となるような光学系を設計することで HMD の奥行きを大きく削減することに成功しました。
This is a developed light field HMD and its specifications. In this HMD, elementary images are generated in real time according to the movement of the HMD and are shown on the display. These images and the lens array reproduce the light rays of a 3D scene in the same manner as in the real world, enabling the viewer to view natural 3D images. These are 3D images displayed on the light field HMD. Because an optical image is formed in space, when looking at the foreground appears to be clear and the background appears to be blurred. This is a common way of seeing in the real world. However, with conventional HMDs, the focal position of the eye is fixed regardless of the depth position you are trying to see. I will introduce our research into ultra-thin, lightweight, flexible displays and OLED films, which we are working on to build 8K sheet type large screens that cover the entire wall, as well as light and bendable flexible displays. We are conducting research on large, ultra-thin, and flexible displays so that viewers can easily manage large screen displays and enjoy UHD TV at home. As part of this research, a prototype 30-inch 4K flexible OLED display that can be rolled up was fabricated in cooperation with a device manufacturer. This display was 0.5 millimeter thick and weighed 100 grams, excluding the driver. It was created by forming OLED elements with high precision that glow red, green, and blue on a thin plastic film. This is a 60-inch 8K flexible display made by tiling 4 30-inch 4K flexible displays. We have developed a technology with the aim of improving quality to compensate for variations in photo emission, such as those resulting from burn-in. A bendable electroacoustic transducer is attached to the back, and the sound is emitted from the screen itself. The electroacoustic transducer, along with the display, can be rolled up together for compact storage. We developed a variable curvature flexible display with 3 tiled 30-inch 4K flexible displays. You can use a flat display when watching with many persons and a curved display when enjoying travel videos or games by yourself. It is possible to enhance the immersive feelings and sense of reality by combining with a haptic chair device that vibrates together with the video. Please look at the explanation video of flexible display.
これまでにさまざまなスタイルで手軽にコンテンツ視聴を楽しんでいただくことを目指して丸めて持ち運びできるフレキシブル有機 EL ディスプレイの研究開発を進めてきました。この展示ではいくつかの試作例をご紹介いたします。まず最初にメーカーと共同で開発した30インチ 4K フレキシブル有機 EL ディスプレイです。30インチのパネルサイズでありながらパネル部分の厚さはおよそ 0.5mm、 表示部の重さはおよそ 100g です。薄いプラスチックフィルムの上に電流を流すと赤、緑、青それぞれに光る有機 EL 素子を高精度に形成することで実現しました。この技術をもとに将来的にはスクリーンのような大画面でも丸めて収納できるディスプレイの実現が期待できることに加え、視界を覆うような円筒型やドーム型など没入感を体感できる VR ディスプレイにも応用ができると考えております。これらの技術を応用し試作したロール収納型ディスプレイです。極率半径2センチで装置内部に丸めて収納しております。このようにフレキシブルディスプレイを用いることでリビングルームに設置された大型ディスプレイも未視聴時にはすっきり収納することが可能ですし、移動や設置も容易になります。次に30型 4K フレキシブルディスプレイ4枚をタイリングした 8K フレキシブルディスプレイです。ディスプレイ同士の明るさのムラをなくす技術や時間経過により生じる焼き付きなどのムラを軽減する技術などを開発し、均一な画面表示を実現しました。また背面に電気音響変換フィルムを貼り付けているため、発生する振動により画面から音を出すことができるだけでなく、ディスプレイと一緒にコンパクトに丸めて収納することもできます。昨年の技研公開では没入感のある湾曲型 VR ディスプレイを展示いたしましたが、今年は曲率を変化させることができるディスプレイを開発しました。これによって家庭など複数人で視聴するときにはフラットに、また湾曲にすることで個人でオンライン会議などに利用するとき、その場にいるような緊張感を得ることができます。旅行の映像やゲームなどを楽しむ際は椅子型触覚デバイスによる映像に合わせた振動により没入感、臨場感を高めることができます。
We are currently researching thin and soft OLED to fabricate a display whose shape can be changed. Ordinary OLED cease to emit light upon encountering a little moisture. Hence, we have developed an OLED that can emit light for a long time, even in the presence of moisture, using a unique material that can supply electrons without using alkali metals. This OLED emits stable light even when a thin and soft film that is permeable to moisture is used as a barrier layer. This feature has been utilized to create an OLED film light source with a thickness of 0.07 millimeters, which is thinner than paper. Currently, it does not have a pixel structure like a display. We will continue to conduct research with the aim of applying this method to large screen displays. We are researching stretchable displays that can be freely shaped. To fabricate stretchable displays, it is necessary to fabricate thin film transistors, TFTs, and light-emitting devices on stretchable substrates. Here, we demonstrate stretchable metal oxide TFT irons on polyimide film. The part that appears transparent is the elastic substrate, and the part that appears yellow is the metal oxide TFT. The stretchable metal oxide TFT array is pulled sideways. The TFT array stretches by 50% and 100%. We evaluated the characteristics of the developed stretchable TFT array. The figure shows that even after stretching from 0% to 50%, the characteristics remained the same as before stretching. In the future, we will explore elastic wiring materials that can connect individual TFTs. We have exhibited some examples of our display research. We hope to deliver a novel experience that expands beyond simple viewing through viewing styles using various viewing devices. Through R&D efforts targeting new broadcast media services for 10 to 20 years in the future, we will continue to meet these challenges. Thank you very much for your attention.
So thank you, Mishina, Dr. Mishina, for your nice, great, keynote to speak. Okay, let's move last keynote talk. Last keynote talk will be given by Professor Dr. Mike Heckmeyer, and Executive Vice President of Display Solution of Electronic Business, Merck, Germany. Let's welcome Dr. Mike Heckmeyer. Let me brief introduction of his autobiography before start his talk. Dr. Mike Heckmeyer have received a PhD in physics. Then he joined Merck, and Mike Heckmeyer is Executive Vice President and Head of Business Unit Display Solution at Merck. He leads the global display solution business, consists of liquid crystal, OLED, and photoresistor, but also some explorative new business area like liquid crystal window or antenna. Mike is a member of the electrical business global leadership team at Merck. He's also the member of Baden-Baden Enterprise Association since 2013. He's also the owner and co-author of over 150 patent applications and from per Merck. Okay? Please start.
Thank you, Chairman. Good afternoon, everybody. Thank you for attending. Thanks to the organizers for inviting me. As you heard, I'm running the display business at Merck, and welcome to our presentation, Advancing Display, Advancing Life. So Merck is a very rich history company. So we have 354 years of experience, and I'm very happy to introduce the company to you. So we run 3 business sectors: healthcare, life science, and electronics. So this text doesn't run. So our business in electronics is structured in 3 business units: semiconductor solutions, display solutions, and surface solutions. And today, of course, we focus very much as a major provider of materials to the industry on sustainability, and we want to fulfill that every day. So before we dive into this, let me explain a little bit more about our approach here. So this is our product portfolio, and we're offering all materials to display industry: liquid crystals, OLED, photoresist, reactive mesogyns, and siloxane, other backplane materials, but also, as we heard earlier today, quantum materials getting more important to the industry, and that's basically another area we are focusing on. So displays, as we know, matters a lot. So 80% of our perception is with our eye. And that means the display and the display industry is vital to govern literally all of human perception. Combining that with the other statement here that 6.6 billion smartphones are in use in the current year, you can of course easily imagine how important the display and our work here is for mankind. So it's the most important interface between humans and data. So what are the key trends in the display industry? We heard a lot about this already from previous speakers. High resolution, high transmission, faster switching still requirement, transparent, bendable, just in the last one. And this is what excites us every day. One aspect, let me particularly highlight, it's the Green Deal, and it's that we need to make the display situation more sustainable for all of us. So we have a lot of experience, so with more than 130 years of experience in liquid crystals, and more than 50 years in liquid crystal displays, of course, this is a very rich history, and Merck developed numerous innovative technologies and products in display and beyond displays. But, of course, OLED very clearly is the future trend, and we have also more than 20 years of experience in OLED in the meantime, and we are qualified in most of all major OLED products. And of course, this is super exciting to shape those trends of the future as well. Digital optics, AR, VR, you heard it, and we can just reiterate and emphasize the key technology of the future. And eventually, this will lead to a relaunch of certain liquid crystal materials, what we call the so-called RM materials. Yeah, so digital optics will support the trends to AR and VR. And while the electronics industry is probably still several years away from commercialization of such device, the overall route is very clear. And this is why we maintain a large portfolio of those reactive mesogyns already today. And we are working with our customers on sustainable solutions to enable these glasses that will be increasingly comfortable to wear and which sooner or later will display very natural feeling virtual images. So now coming back to sustainability, and we are all feeling the effects of climate change. Earth is heating up, extreme weather changes have intensified floodings and droughts globally. And in Seoul, there were heavy floods just a few weeks ago, right? So this picture now shows, I think, a very scary situation. This is a bridge over a river in Portugal, southern Europe, but you don't see any water, right? So according to most recent UN climate report, it's now or never to limit global warming to 1.5 degrees or 2.7 Fahrenheit. As a father, I don't want to have my kids experience a world of unprecedented heat waves, widespread water shortages and food shortages. So the next slide here, of course, this is really, really concerning. It's likely that the Arctic will be ice-free in the summer pretty soon. So there will be substantial habitat losses for Arctic animals such as polar bears, whales, seals, and seabirds. And it will get hotter and hotter. So heat waves that now occur every 10th year will approach becoming an annual event under 3-degree scenario. We at Merck recognize this urgency and took already some action for being a part of the solution. I'm a very frequent traveler to Korea, and I can tell you this time is the first time ever that in Germany it's warmer than in Korea in August. So can you imagine? So what are our goals to kind of contribute to this? So we have clear roadmap. By 2030, we will approach 1 billion people with our science and technology innovations by Merck. Also by 2030, we will integrate sustainability in all our internal processes, no matter R&D, CapEx, supply chain, it will be everywhere. And we have a very clear commitment that by 2040, as a company, we will be carbon neutral. So our environmental sustainability focus areas in the display business is reflected here. So we focus very clearly on a holistic approach. So each one here has a role to play. And this is very well summarized on this slide. So for a typical smartphone, assuming lifetime of 3 to 4 years, the CO2 emissions is around 50 to 80 kilogram. So this is like 160 driven miles. 80% of emissions is in the smartphone case coming from manufacturing the phone, 20% from device usage, logistics, energy use. So the emission reduction need to be contributed by all the players in the value chain, including device maker, material suppliers, but also raw material supply chain. As there's a strong push for green commitments from the whole value chain. So in our display business, we are focused on several key areas to enable our customers to go greener. From investing in making our sites sustainability ready to reduce our CO2 emissions, waste and water to energy consumption. So let's have a look at some examples here. So if TV resolution moves from 4K to 8K, LC technology needs to step up in transmission to meet energy efficiency guidelines. So this is where the new UB Plus technology delivers a clear breakthrough. 15% transmission improvement over conventional technology like IPS and FFS. So this leads to lower energy consumption as well as CO2 emissions. 15% less energy consumption of all TVs worldwide can lead to CO2 savings equivalent to 900 airplanes average distance flight per year. So what about OLED? OLED, we are supporting our customers to make sustainable OLED structure like the two-stack RGB tandem OLED. With this structure, the brightness of the panel doubles while its lifespan is expected to quadruple for tablets, notebooks, and other automotive applications. So the application of this technology also reduces power consumption in smartphones by up to 30%. So what's coming out of research? Deuteration, another key technology we are working to realize next generation of OLED. So deuterium is an isotope of proton, it's heavier. The atomic mass is double compared to proton, which is why it's also known as the heavy proton, right? So higher atomic mass increases the activation energy for bond dissociation, which means the bonds are difficult to break. A deuterated material compared to non-deuterated material has lower zero-point energy, making materials more stable. Since the activation energy to break the bond is higher, materials degradation process is slower. So therefore, deuterated materials have the potential to more than double the lifetime of OLED stacks without compromising efficiency or voltage. So in general, we observe increased lifetime with higher deuteration degrees of the material, and we are working with our customers to enable this with our OLED materials. We focus on high purity, responsible consumption of those new raw materials. Supply and process robustness, of course, for such new material is a must. So with our deep understanding of the display industry, along with strong collaboration of customers, we enable eventually the perfect stack for any application with constant improvements in efficiency, lifetime, and other specs. So for example, by steering the charge flow across the OLED stack with our broad portfolio of transport layers, so this is done while maintaining easy processability during production. We also go beyond organic materials that make the OLED stack. We offer innovative solutions that are the key for flexible and foldable displays, for example, in thin film encapsulation or flexible hard coat materials. So to enable these devices, the display materials must be 60% thinner compared to standard displays, and they will have to be robust to prevent display stress caused by continuous folding and rolling. So our LiviFlex materials are designed to provide a very thin yet robust protective layer. Our solutions can be used in rigid devices as well, and we're paving the way for more. So another example, so it's where smart antenna is innovation, very exciting for everybody. What used to require complex and sometimes mechanical steering solutions for antenna is now done with smart liquid crystals. So this can electronically steer an antenna beam in the desired direction and thus enable radio connections with high data rates and high frequency. The liquid crystal-based solution enables energy and cost-efficient antenna terminals for satellite and internet access for a larger population, even in remote areas where affordable broadband internet is not available today. Further application of liquid crystal, of course, are the windows that can be dimmed just at the push of a button. So the technology by Merck here makes this possible. Through intelligent light and heat regulation, our windows open up completely new architectural possibilities for the development of sustainable buildings. And this technology enables energy saving up to 10%, also leads to improvement in health and productivity of people who live in such rooms which are framed by such windows. So a productivity rate goes up by 5 days per year. And first projects already implemented very successfully with a rich pipeline being built up now. So what's happening on the back plane, our patterning materials also move into the direction of energy saving. Low temperature processable positive tone photoresist already used to pattern on-cell touch sensors. And these sensors enable a thinner display structure, which is crucial for foldable devices again. So on-cell process with Merck's dielectrics can simplify lamination, replacing CVD to some extent, and coating process consume less energy. The energy saving aspect on the thermal process is another great example of our contribution to help the supply chain towards a sustainable future. So in the end, we can only advance digital living if life is sustainable. So if you're interested in learning more about this offering in some detail, also my colleague Johannes Canisius has a session later on sustainability that you can attend. So Merck's association with Korea is a very long one, and we started our operations in 1989, so 33 years ago. We opened a liquid crystal research center a year after that, when the LCD industry was still in a very early day. At the same time, Korea was a country that realized the possibility of commercialization of liquid crystal. So we decided that we could open the market together through a strategic investment. And very early on, we established a factory that offers a stable supply of display materials for domestic display companies and a display research center that contributes to the development of state-of-the-art displays. Korea is a major innovation hotspot and one of the most important OLED growth markets. And we are fully committed to keep investing in the country. So our goal is to become the most localized global partner and provide holistic solutions from research to production right next to our customers. So what does it mean? Early this year, as part of our growth program Level Up, we announced to invest 600 million euros into Korea in the next couple of years. So this will further strengthen our semiconductor and display capabilities and enhance local activities dramatically. We already have great capabilities in Korea with our broad display materials portfolio, local R&D, manufacturing, and servicing our OLED materials, liquid crystal materials, patterning materials, and quantum dot materials. To further support Korea in leading the global OLED market, we have an advanced OLED development lab and OLED application center in the meantime. So this is now complemented by OLED sublimation fab in Posung. Our targeted localization in Korea ensures that supply is continuous and stable. So in the meantime, Merck is present in 11 sites in Korea with more than 1,500 employees. So quality and purity of OLED materials are two of the most important factors affecting the performance and lifetime of these devices. So to deliver high quality, high purity materials with the desired performance level, we've invested another 25 million euros to install sublimation equipment, vacuum deposition, process simulators at our OLED application center in Posung. Adding OLED process simulators to the development process will enable us to study the correlation between OLED materials and processes, which occur in the deposition process. So can we start the video that you can get some impression of this? Shall I start from here?
Yes, please start.
Let me try.
Free as a bird in the sky, that is what you are. Breathe and you know you're alive. Feel the beat of your heart. Well, life is a crazy way of turning everything upside down. So move with the time that you have. The world will keep spinning round. Don't wait for tomorrow. Live for today. Keep chasing the sunshine and go out and play. Listen, I wanna be there with you no matter where you go. Life is a table for two, and we're starting the show.
So lots of happy faces working for OLED here. So, looking ahead, and Dr. J from Samsung mentioned it already, a smart world of everything being smart, boundaries are blurred between traditional industries. So chips, advanced displays enable exciting new applications everywhere and together. So this technology convergence is great news for all of us. And we support this with massive investment in Korea, as mentioned already. At Merck, we are ready to walk the talk, to be fully committed, support the industry to enable future trends of tomorrow with our sustainable materials and solutions. So we think we are at a critical junction in time and requiring all of us to make choices to stop the effects of global warming. Environmental sustainability is of high relevance for the display industry, and it's one of our key priorities. So we are addressing sustainability from multiple angles, emissions reduction, waste reduction, but also energy consumption is, of course, very critical. We also look forward to strong partnership with our customers and the industry. The global environment continues to be volatile. Supply reliability and continued innovation is key to keep the market winning and going. So together, we hope to solve the complex challenges and to advance display and advance life. Take care, stay healthy, and thank you very much.
Thank you again for your great, keynote talk, Mike Hengmeyer. So now the time for closing this keynote session. Thanks again for your joining and the welcome and also the keynote session. I hope all of you enjoy the beautiful Haeundae Beach tonight and hope to see you, all of you, in the conference room tomorrow morning. Thank you.